Okay, let's start. Great. Okay, so couple things. One is we're going to have an exam on February 27th. Exams are one of those minor inconveniences for these classes. Okay, the key thing is for you guys to learn all the principles and all the programming details, and make sure that you can really do parallel programming efficiently, correctly, and so on. But I need to submit a grade at some point. So so we all go through this exercise. So that's why I want to make sure that when you take the exam, when you prepare for the exam, you actually are working on the things that I want you to learn after you finish the class. Okay, so that's what the study guide is about. So take the study guide seriously, and we also put our previous exams on the web page so that you don't have to sweat too much over these exams. On the other hand, the exam is not going to be totally trivial, so you will have to think about these things a little bit. So I'm not going to be here on that day. I'm going to be in Europe for a meeting. So the TAs are going to be here to administer the exam. And our best advice is that study all you want, before the day. And on that day, don't spend much time on this. If you were going to spend some time in the afternoon studying, take a nap instead. Okay. And it really helps you come in with a fresh, refreshed and ready to think, already digested the material, and it will be a great time, because that's the exam. It's only about 10 days away, so you really should be putting things together in the next week or so. Okay, that's the exam. Any questions about the exam? Yeah. The exam is going to be very similar to the exam that you're going to see on the website. So it's going to be 5 questions. The first one is short answer or multiple choice for concepts, and then there will be 4 more or less applied kind of things. One on the basics of CUDA, one on matrix multiplication type of problems, one on convolution type of problems, and one on probably something else. Okay, so application. So if you look at the previous exam, it's going to follow pretty much the same format. Yes.
Do we get a form of cheat sheet?
Yes, you can bring a cheat sheet, and we would like you to limit your font size to no smaller than something like 7 or something, 8 or 7. Okay, it's for your own health. So you really shouldn't have to do too much. We're going to give you most of the things that you need, so that you don't have to really memorize everything. But if you want to bring cheat sheet, 1 page, 8 by 11.5, 8.5 by 11, I believe, and both sides. Okay. Any other questions? Okay, good. And for Chicago, we're going to experiment today and one more time next week to make sure that we have a mechanism to kind of put together a mechanism for you to ask questions easier. So I'm going to ask the audio-visual people to keep the channel quiet until you push the button to ask a question, and I'm hoping that Carl will be able to hear it from here in the front here, so that he can relay your question. I want to make sure that the questions that you have will be you can ask the questions in a timely and easy way. I want to introduce Carl here. Carl is my senior grad student, and he has been with me for a long, long time. He has been teaching various courses with me worldwide, and one of his favorite events, according to our past conversation, is we teach a summer course in Barcelona in the summer. And if you do super well, I may take one of you to Barcelona in the future. So Carl is preparing for a faculty position, and so he's he's in the Mavis future faculty program here. That's why he actually put together some of most of the machine learning material for 408 in the previous 2 semesters. And he has already satisfied all his requirements for the Mavis Fellowship program. So we're not going to get him to do heavy lifting work for the course anymore. But when I go over this, we're still improving the slides and materials. So I wanted Carl to be here so that we can figure out how we can evolve some of the slides in the future. Okay, and Carl will also be still somewhat involved in the class, and so I want you to see, when you see some posting from Carl and so on, here's the face. Okay.
Yeah, when you have inevitable problems with the project, who to be mad at.
Exactly. In fact, Carl is responsible for designing that whole, final project, and he and another student, Abdul Dakak, they designed the right infrastructure. And some of you asked me the question, will we be able to test our own CUDA code, and we'll be able to use our own data set? I said, yes. Okay. When you start the project, you will be able to do, pretty much all the any type of CUDA development using the right infrastructure and still run your GPU code in the cloud rather than your laptop. So no worries. Once you learn all these, labs from the basics, you will be able to exercise all you want, for the rest of the semester. Okay, so that's kind of, the logistics that we're going to make. So we're going to continue, and we're going to have 3 lectures worth of machine learning. We got a little bit of a head start last time. I introduced the, sort of the basic machine learning concepts, and then, we stopped at pretty much this slide, where we say, hey, the machine learning was very popular in the 1980s, and neural net was actually also very, very popular in the 1980s, but then they died. And so I'm going to go through some slides today to essentially give you the historical sort of the perspective, and then walk into the implementation of the deep learning networks. So GPU computing, why do we have so much attention and so much resource spending into machine learning and deep learning today? The primary driving force of this whole movement in machine learning and pushing machine learning and artificial intelligence forward with machine learning is because GPU computing hardware and these programming interfaces, primarily CUDA, that you are learning here, has enabled very fast research cycle for training of the machine learning models. So these things have been very effective in machine computer vision, speech recognition, document translation, self-driving cars, and data sciences. And these are high-value applications that we have not been able to do, to have effective systems. And then because the GPUs are enabling us to process a huge amount of training data when we train these models, suddenly these things have become practical. And most of them involve logic that we previously were not able to effectively construct with imperative programming. So if we know exactly what the algorithm is, if we, for example, for sorting, we have had decades of experience defining the exact algorithm for sorting, right? So we have, when you learn that, take the algorithm class, you have all kinds of variations of sorting, some with more parallelism, some with less parallelism, some with higher algorithmic complexity. Some of them have lower statistical algorithmic complexity and so on. So we know these things very, very well, but there are problems that we don't know well enough. And using sort of a big amount of label data to train and specialize these, the deep learning neural net, what essentially can derive a large quantity of quality labeled data in this whole process is the major challenge. So essentially, whichever application domain can produce cheaply a large amount of labeled data, that application domain have a real shot, applying machine learning techniques to in their applications. So let's go into the the very basics here. Many of you have, I hope all of you have taken a logic design course. And there's a reason why both ECE and CS students need to take logic design course. Because fundamentally, when we program, when we design computing systems, when we do anything, it's actually the foundation for everything that we do in computer engineering, computer science. And there are two fundamentally different logic. One is the combinational logic, and one is sequential logic. And if you look at machine learning, neural net designs, there are also two categories that are directly related to these two logic categories. So we have the feed-forward networks, and then we also have the recurring networks for exactly the reason, because they actually are more or less formulated in the same manner as logic design. So we're going to start with just combinational logic, which corresponds to what we call the feed-forward networks. So when we design a system, what we need to do is we need to have input and we need to have output, right? So the input and the output essentially defines what we need to do. So a combinational logic essentially defines the relationship between the input and output without memory in the system. So the input at any particular time completely determines what the output should be. And so here we show a simple piece of very, very small system with three input bits, right? Three input bits, A, B, and C. So by defining all the 3-bit combination patterns, which is 8, right? 8 of them, 0, 1 for each one. So we say that this system has 3 degrees of freedom, right? 3 degrees of freedom. A, B, and C are each 1 degree of freedom. And each degree of freedom, we have 2 possible values, 0 and 1. So this gives us 2 to the third possible combinations, right, with those 3 degrees of freedom. And then we can define output. In this case, we define output bit 0 or 1, right? So we have this truth table here that specifies for all the 8 possible input bit patterns, the output, the desired output value for every input pattern. And then we can realize this truth table with a gate array like this, and we can, so this is a very straightforward hardware implementation of that truth table. And this hardware implementation will give us exactly what should be done with this piece of logic, okay? So that's great. What if we didn't know exactly what the truth table is? So, it could be that, we know that we want to have, a piece of logic, and we don't know the outcome. We don't know the outcome of every possible combination, but we know some of them. Okay, we know some of them. So, so the question is, can we look at enough observational data to construct the rule? Okay, so let's say someone says, okay, you get a user of the logic here and say, okay, here are some input combinations, 0, 1, 0, 0, 0. Tell me what this output should be. And then the user look at it and say, okay, 0, right? And then you say, how about 0, 1, 1? Tell me what this piece of logic should produce. The user says 0. So the user may not know exactly how to design this logic, but the user knows what's the desired pattern if you give that pattern to the user and say, look at it, and what do you want that to be, right? So let's say we collected 4 of these inputs, and we got the user to give us the expert opinion about what the output should be. So these are now we have these 4 pieces of data. Does this completely specify the logic? Probably not, because we really need to have all the 8 to be able to completely specify the logic. But if we design a piece of logic with these 4, we will be able to do correctly with these 4, right? And But if we have an output that we did not cover, then it's kind of random, isn't it? So, you know, then it depends on the fate. So this is, you know, the foundation for any of the feed-forward network. If we have enough observational data that covers all the input patterns or cover sufficiently big amount of the input patterns, we can construct the truth table and derive the logic, or derive a logic that operates close enough to the exact design. Okay? So, you know, that's the whole point about, you know, this machine learning kind of feed forward, what we call the feed forward approach, you know, with this. So you said, okay, if that's so simple, why are we spending so much time studying these things? You know, why do people pay millions of dollars, billions of dollars buying companies doing this kind of stuff? Here's the problem. The problem is the logic formulation. You know, if we just take that logic formulation and try to, you know, strictly apply that, we can potentially take any kind of input, right? A picture is simply a collection of pixels, and each pixel is only 8 bits. So we can just treat it as a, you know, whatever number of pixels times 8 bits input into our system, and then we can specify what are the output, you know, lines. For example, we want to say line 0 is human, line 2 is, you know, dog, line 3 is a staple, you know, a stapler, and so on. And then we can just have a complete implementation of that if we have enough data, right? That, you know, which is true. So the logic formulation of a, let's say, 32 by 32 pixel image. This is a very, very small image. If you only have 32 pixel by 32 pixel, your iPhone is producing a picture of what? About 12 meg these days. So in fact, you know what? It's usually a few K by a few, like a, you know, 4K by 4K or 2K by 2K kind of picture, right? So 32 pixel versus 2K on each side, 32 on each side. It's a tiny, tiny, small picture, right? So, but you know, let's say for the moment we're happy with the 32 by 32 picture, and we're going to recognize the objects, okay, in that 32 by 32 pixel picture. So if we do this, we're going to have 1,024, right? 32 by 32 will have 1,024 pixels. And then each pixel has 8 bits, right? 8 bits. So we have 9,000 and 8,190, no, 96, I believe. Total bits as the input, right? So 8,196 bits of input. Remember, each input bit represents a degree of freedom. Remember that? Okay? So we actually have a truth table of 2 to the 8,196 entries. How big do you think this number is? So I want you to do an exercise. How many billions of people do we have on Earth? 7 or so, right? About 7 billion, 8 billion, maybe approaching 8 billion. 8 billion is roughly, you know, 2 to the 32 times 8. Okay, so 2 to the third. So it's about 2 to the 35. If I have this amount of money, and I'm very generous, I give everyone, I just share this money with every individual on Earth. Okay, on Earth. That means that I'm going to divide this amount of money by 2 to the 35, right? And each person will end up with 2 to the 8,161. Okay, and if that person shares that amount with all the 7 billion people, it's going to divide by another 2 to the 35. That's going to give you 2 to the 8,130 whatever, right? 20 whatever. And this is a serious amount of money. You can do this forever, a long, long time, and everyone still gets much more money than what each person will ever earn, okay? So there are lots of entries in this, okay? Really, really a lot of entries, okay? So, but this is only a small picture, right? Only a small picture. So if we want to use the brute force approach and have a complete, accurate solution, the number of cases, right? The number of pictures, each picture will give us one entry, right, in that truth table, and you need to have someone to label it. The flip side is, if we get everyone on Earth to work diligently on these labels, the people will all be, working on this full time for the lifetime of each person, and we will still not be able to produce enough label pictures. Okay, so that's how hard this thing can be. So if we manage to collect and label 1 billion images as training data, 2 to the 32, I already went through the exercise. We could only cover 2 to the 32 over 2 to the 8,196, entries of the truth table. So this barely even moved the label, this needle as far as the portion of that truth table that you can cover. So obviously this is not going to be possible. So that's why all these machine learning mechanisms eventually depend on something called features. Okay, they all need to have some kind of more generalized form that they can rely on to learn these patterns, and hopefully learn a huge number of truth table entries in each label data to be able to to have the hope to cover any significant portion of the possible outcomes. Okay, so this is something that you always need to remember. So let's go into this a little bit and say, okay, back to our truth table. What are the features for this truth table for this particular application? It turns out that we can tell that this is, if you, as a human, you'll be able to see that this is exclusive OR. Okay, this is an exclusive OR logic. Whenever you have an odd number of bits, 1 bit in your input, you're going to have an output 1. So one of the features that you can use to learn these things is that, there's several types of logic. Some logics are detecting odd number, even number of ones. So whenever I see an input of 2 to the, let's say 2 to the 8,196 bits, I do a quick addition. Okay, I do a quick addition and see if I have an even bit or odd bit, and that will be one of the features I will try to extract from that picture. And then I'll say, okay, if it's even, if it's odd of ones, I'm going to have an output 1. Does this really specify the logic? Not really, because we didn't say anything about the bit patterns with even number of ones, right? So that that would be left for interpretation. So we can also say, okay, feature 2, if all the bit patterns are even ones, then we say they have to be 0. Now we have nailed that particular piece of logic, by learning. So if we have enough of these labeled inputs, and we saw that all the inputs with odd number of ones were labeled 1, okay, and all the even number of 1 inputs are labeled 0. And if we have enough of them, we will learn that, oh, this is a feature. Okay, so we're hoping that whatever mechanism we have will learn and say, okay, here is a feature that we're going to use. And then when the fresh inputs come back, we will use those features rather than trying to have some kind of random logic to figure out, right? So that's the reason why these features are so important. These features are really used to reduce the dimensionality or the degree of freedom that we have in the input, and reduce that into a much more feasible amount for learning and for inference in practice. Okay, so we're going to see for the reason why the neural nets are so popular now, the deep learning are so popular, because they are able to enable us, they are able to extract some of these features from the data on a automatic basis. So this brings us to the sort of the space of problems, and many of you have taken all these courses, algorithm classes, data structure classes, and then you have already learned algorithm complexity, and then hopefully you have learned now parallelism and so on. So when we look at these human problems, the problems that as a programmer, as a designer, that you need to solve, we oftentimes have this two-dimensional description, space description of problems. And we say that the problems could be easy to describe, or essentially the solution to these problems are easy to describe as an algorithm, or hard to describe as an algorithm. So some of the problems we know exactly how to solve. Okay, so we can very easily, when you take a 374 class, you will be able to take an exam, and then you'll be able to describe exactly how you're going to sort a list of elements. Okay, so that's relatively easy to describe. And then you have easy to perform and hard to perform. These things are measured probably in terms of algorithm complexity, and probably described as parallelism that you can get, and probably the locality that you can have in order to save bandwidth when you do the compute. So these things ultimately determine the amount of time that you will need to spend in order to solve these problems on a computer. So we can look at your ECMPs. So far, you have matrix multiplication, you have convolution, you have vector addition, and these things have various computational complexities, but they're all relatively easy to specify. Okay, you are able to write the kernel code with a small amount of code, right? And the matrix multiplication has high computational complexity because it's a n-cube algorithm in terms of the dimension of your input matrices. However, compared to exponential kind of things, it's no big deal, right? And on the other hand, vector addition is purely linear algorithm. Okay, extremely easy to perform, right? Matrix multiplication is easy in the sense that we already have techniques that we can impose. We can do things in parallel. We can generate output elements in parallel. We can impose some discipline into the data access and reuse data so that we can perform the computation with very small amount of memory bandwidth, right? Use the memory bandwidth. So we can compute matrix multiplication on a practical device today extremely fast. Okay, so that's why these things are easy problems. Okay, easy to describe and easy to perform. It's not easy, 50 years ago, because they have not developed some of these techniques. But with all the knowledge that we have today, by taking these kind of classes, you know exactly how to solve these problems efficiently. So we call them easy problems now. We have these other things, okay? So, for example, some of the things are much harder to formally describe. Things like recognizing, spoken words and facial detection kind of things. These things are very, very hard to describe with formal algorithms. How do you write a formal algorithm to detect all the faces in the class, right? So, after 30, 40 years of research by, very capable researchers in our, academia industry, we still don't have a good formally described algorithm for facial detection, right? So that's hard to describe. But, once you describe anything, they're relatively easy to compute. Okay, the computation tend to be, somewhat, easy in terms of the parallelism and so on. And we can easily divide up the pixels, and then we can do certain things. So on the other hand, there are certain things such as chess that is actually relatively easy to describe, and you can even write a piece of code that is supposed to give you exact solution. But the exact solution has extremely high computational complexity, right? That will not be able to get the answer in a reasonable amount of time. So that's chess. And then we have the upper right corner, which is essentially the holy grail, okay, of computing. So how do we do the literary analysis of all the literature and then all the papers and all the publications, and how do we do international diplomacy, diplomacy, and how do we actually handle all the intricate problems involved in that whole thing? And this is actually becoming this becomes a very complex network of game theory kind of things that interact with each other, and then the complexity simply explodes if you try to do any kind of solution. So let's take a look at the historically the AI success, and this was really pioneered by IBM. Okay, IBM had with a long history of solving chess problems, and there's something called Deep Blue that IBM's invested decades of effort trying to beat the human champions. So the chess problem is relatively easy to formalize. In fact, I was never a good chess player because I didn't have the patience to actually sit down there and then play enough times to make it to be a good chess player. But early on, I realized that I can write a piece of code. So I just write a piece of code, and then and that piece of code was not very good, for obvious reasons, but it actually beat most of my friends. So that was good enough. Okay, so then I said, okay, I don't need to be a good chess player. I just bring a cheat, a little bit of cheat, and beat my friends and impress them anyway. So on the chessboard you have 64 locations, okay, and you have 32 pieces. So the state of the of the game is relatively easy to characterize, and also you have rules. You have very well defined allowable rules. So you can write a piece of code that that obey these rules and make all the possible moves, and you can score each configuration, right? Each configuration is in your possibility tree is at the leaf is a possible board state, right? So you could proceed down the path that results in the best position that you want, and one of them is, or some of them is going to be checkmate, mate, right? So these are the kind of things that you can do. So, but these things are hard to perform. Okay, you have about 30, on average, about 30 legal moves per position. So every time you look at a board, there are about 30 possible legal moves on average. Okay, some of them are more, some of them are fewer. And if you want to go down about 10 steps, you want to think ahead 10 steps and see the consequence of your moves, you would you need to actually perform 1,015 moves evaluate 1,015 moves for 10 kind of step ahead. And this evaluation will take about 30 years at about 1 million positions per second. So if you can do 1 million positions per second, and then on the computer, and 1 million positions a second is a lot. It's a lot, right? But then you need to spend 30 years to evaluate. Obviously, that's not going to be good. So several things. One is you need to start to have heuristics. Okay, you need to introduce some heuristics into the system. You need to say, okay, some of these are probably dead ends. Cut them off, and then you need to parallel search. That's part of the reason why IBM's invested tremendous amount of effort building the blue jeans computer, and one of the driving applications is this very, very parallel search of that space and the fast computers. So finally, IBM has reached the point in 1997 to be able to search the space fast enough. Okay, everyone already know how to do this, but in 1997, finally, the Deep Blue was able to defeat, Kasparov. And that was a very famous match, right? So, did we really solve the problem? It's relative. So this is this brings us to a very important story for engineers. Okay, there are only a few important stories for engineers to know, and this is one of them. Okay, there are two friends who are taking a walk in the wild, enjoying the scenery, and out of nowhere comes a big black bear, and the bear was charging very, very fast at these two friends. Okay, so one of the friends said, "Oh, we're doomed." The other friend said, "I'm going to run," and the first friend said, "Why do you bother to run? Look at how fast that bear is running, right? We're doomed." The second friend says, "No, we're not. You are. As soon as I can outrun you, I'm good." Okay? So here we have, one friend, which is, Gary Kasparov, and the other friend is Blue Jean. Okay? Neither is very good. Okay? Neither is very good. The human used to outrun the computer. In 1997, the situation changed. The computer outran the human. Whether or not either one is very good is not the point. The point is one outran the other, so one will survive and the other one will have to be eaten, right? So this is one other thing that we need to remember. When we design a system, oftentimes it's not about whether the system is ultimately good. Oftentimes it's about whether the system is going to be better than any of the alternatives enough. And this repeats again and again when you look back, when you look at iPod design, if you look at iPhone design, if you look at the various products, if you look back, those things look terrible. But they were sufficiently better than the alternatives that they were immensely successful, right? So this is now whether or not these systems are going to be truly have perfect solutions to these problems is not the point. The point is, are these things going to be able to do better than all the alternatives that we have at our disposal? And when you think about self-driving cars, when you think about facial recognition, when you think about all these other things, that's going to be what's driving this. Okay, so here is a interesting kind of a history about what we call the traditional AI and the kind of the machine-based, machine learning-based AI. So there's a kind of a the approach called the psych, and it's a approach that tries to do comprehensive ontology and knowledge base of common sense. Okay, so essentially the assumption is that if we put all these rules, all these kind of the important things that we think through every day into the computer, and let the computer do all these kind of inference and then combining rules and so on, and then when the computer is facing a kind of a challenging question or problem, the computer can just go through all those thinking and then come up with the answer. So this is, the idea is that if we spend enough time building all these considerations that we make as humans into the computer, ultimately the computer will be able to think the way we do. So we have these rules, and then we have these statements into this inference engine, and then we come up with some kind of conclusion, and some of the conclusions hopefully will answer our questions. So here's a simple example. The rules is that if an object belongs to a subset, okay, belongs to a subset, and then the subset is part of a superset, then the object will be part of the superset. Very simple, right? And so here is a simple question that Carl had. I'm not responsible for this particular one. So yeah. sorry. Donald Trump is a U.S. president, and then U.S. presidents are U.S. citizens. So these are two statements. These are two observations. And then so the inference engine could just go in and then start to crank, applying the rules with these statements, and then feed the statements into these rules. So Donald Trump is an object that is that belongs to a subset of the U.S. citizen, right? Only a subset of the U.S. citizen were able to become U.S. presidents. Small subset, okay? And then we also say that the U.S. presidents are U.S. citizens, so the presidents are indeed proper subset of the U.S. citizens. So that means that Donald Trump is a U.S. citizen. So this goes through the reasoning, and it will give us some kind of a conclusion. The problem with this is actually very well articulated by Daniel. I need to remember his last name, at IBM a while back. I was talking to him, and then he said, yeah, these things are good, but the problem is these rules and ontology depend on what you're trying to do, okay, what you're trying to determine. For example, in this case, how do you know that how do you know that all the U.S. presidents are indeed U.S. citizens? Have you looked at their birth certificates? Have you, really authenticated their birth certificates? Have you really gone back into the hospitals to figure out that whether those certificates were actually legally, issued, right? And so those are the kind of things that become, that will impose these additional rules and so on that you will need to go through depending on how rigorous you want to be. And by the way, those are the questions that Donald Trump asked personally, okay, in the past. Right, about another president, right? So it's not unfair that people will ask that same question about him, right? So the point is not political here, okay? The point, I'm not trying to make any political statement, but I'm trying to say is when you get these answers, there are a bunch of these assumptions underneath, okay? And so depending on what you're really trying to use your answer for, it may or may not apply. So this makes these things very fragile, and then oftentimes not necessarily giving you what you really need when you get these answers. So, by the way, this is not an AI class. So if you're really interested in some of these things, you really should take an AI class. Okay, I'm just trying to get you an orientation about what you're about to learn in detail, how that fit into this whole space. So here is a very simple example of why some of these things are so hard to maintain, okay? And so you have a bunch of these rules, and then you have some of these sort of the statements. So here are some good statements. People do not have electric parts, right? So I don't run a battery, right? And so I don't have electric parts. Hopefully all these things are operated biologically rather than electrically. Some students did question that, but let's say I don't have electric parts. And the people have razors, while shaving. So when people shave, they have razors. Okay, and then you say, okay, razors have electrical parts. And then you say Fred is shaving, right? Fred is shaving. So these are the 4 statements that you have as facts into your system. And you go into the inference engine, and then so the question is Fred a person while he's shaving or not? Because it could be that Fred has an electrical part, and so then he's shaving, or Fred has a razor. And then the razors have electrical parts, and then so it's not quite clear, from these rules which way it is, right? So you can't really, rule out some of these possibilities. And so in order to get better answer, you need to have, something more specific, right? And so that you can, rule out certain things. So it depends on your answer. The types of usage or use case that you have for these things. There are also other things like, you know, if we can recognize spoken words, and then we have facial detection, we have all these things, can we really solve the higher level problems? You know, if we can recognize all the words, if you sit here, and you know, let's say a elementary school student came into the room, and they will hear every word that I say. Maybe they will understand all what I'm conveying, but it will be questionable, right? The reason why you understand what I'm saying here, of course, you need to understand every word I say, but there are many, many other levels of things that you need to know, the context and so on, that you know in order to digest, right, what I'm saying here, right? So there's so many more steps going from the left to the right, even on the top. So those are the kind of difficulties that would, you know, essentially become challenges to, you know, that the machine learning approach will need to address, and that's why, you know, it's such a kind of a big research area. So the challenge here, hard to formalize the problem, is, you know, we don't know exactly how to, you know, formalize the problem of facial recognition. So the solution is, okay, if you can, don't even bother. Okay, don't bother to formalize the problem. Let the machine learn from the experience what the problem, you know, how to define that problem. If you have more data, it has more accurate formalization. If you have less data, it has less, you know, formal specification. So let the data drive it. So humans, today, even in the human process, we are becoming more and more data-driven, okay, for exactly this reason. Because even humans can no longer formally describe some of the policies and then, you know, why we do certain policy, how we do certain policy. So we use data to kind of, you know, say, okay, here the data shows that, you know, this is important, so we'll have a rule according to that data. So, you know, in the classical machine learning, we need to have human to choose features. Remember, these are the features that I was talking about. Okay, a clever grad student is going to say, "Oh, I want to look for odd number of bits." Okay, and you know, so for facial expression, we used to have all these armies of grad students all over the world, whose primary job is to figure out a new feature, a set of new features that will make facial expression detection a lot more you know, effective and a lot less expensive. Okay, and you know, so how, you know, then we learn how these features are associated with the outputs. So the grad student would say, "Here's a feature," okay, and you know, so then we say, "Okay, let's go through the data and see how this feature allows us to make better output, you know, from the input data." So if you look at the you know, the processes, the rule-based approach was the psych kind of thing, right? You have the input, and then you have, you know, some kind of hand-designed program, which are all these rules that you know, that we program into our system, and then we can the output. But here, you know, the classical machine learning says, okay, we'll have the input. We have grad students who invented all these features, so we extract these features. You know, we evaluate, you know, the features according to the input and see if the input contain any of those features. If the input can contain these features, then we know what output should be, right? So, you know, so mapping from the features to the output, okay, then we're good. So you, from machine learning classes, you have naive-based approach, okay, and you have logistic regression. And these are all, you know, based on human design features. So when you analyze data, you need to know what you're looking for, okay? And then you go into the data and then look for those, you know, the features. And then in naive base, you treat them as independent contributors to the output. They're all equally possible. They're all independent. So you calculate the conditional probability. And for those of you who hated probability, welcome back, you know. So, you know, you can calculate the conditional probability, and Mr. Bayes is the conditional probability champion, so we learn these things from Mr. Bayes all the time. And there's something called Bayesian analysis, right? We do the estimation of things, so we can't escape probability. And then logistic regression means that you need to learn how to weight each feature's contribution. You look at training data, and you say, okay, some of the features are more important than others, right? In your output. So you kind of learn how to weight these features' contribution, and we try to settle on these weights using gradient descent kind of approach to iterative approach to kind of settle into some. And when we talk about training, you're going to see exactly that. Okay, you're going to see how we're going to use iterative approach to be able to settle into some weights. Okay, so one of the things that most people underestimate until they try to apply to real problems is that data representation is very, very important. Okay, and so here is a simple example. So let's say we have a bunch of observational data, and the data is comes with x and y coordinate. So x may be something like age, y could be something like net worth of the person, something like that. So then you can plot the data point and say, okay, the person graduated from college or not graduated from college, right? And something along those lines is perfectly reasonable data analysis. So you may have something that once you plot it, you have a bunch of people who graduated from college in the middle, and then you have a bunch of people who never graduated from college, around it. So I say, okay, let me try to learn a logic, right? Machine learn and logic that if anyone gives me a data point in the future with an age and net worth, I would be able to tell whether the person graduated from college or not, right? So say, okay, so given an x and y coordinate, how can I tell whether the person graduated from college? So say, okay, here. Let's do a cut here. So let's kind of learn a line, okay, with the proper slope and intersections. So anything to the left of the line is going to be not graduated from college. But then if it's to the right, I need to do something else, right? Remember that the truth table, we learned certain things for sure, like if it's odd number, it's all 1, but we didn't say anything about the even yet, right? So here's the same thing, okay? So you draw a line, this is a good line, and anything to the left of, the left up of the upper left of the line will be not graduated from college, and then everything to the right lower part of the line. And it's easy to evaluate because I can just plug in x, y, and then see if it's less than 10, right? And then I can make that determination. But if it's to the lower right, I need to cut out more, right? So I can learn another line and say y plus 3x. If it's less than 15, then it's promising. But if it's greater than or equal to 15, it's not they didn't graduate from college. So I can keep refining this, right? I can keep learning more and more lines. I can learn this line, right? And then I can learn more and more, and then I will eventually get something. But if you look at this, you see that this is something. If you use a radiate and angular representation, and you put the origin in the middle of that blue, and then you do the radius, and then you will be able to have a very simple rule to determine whether the person has graduated from college or not. So then when you do the inference, you need to convert from age and net worth into the origin. So that's what we call the bias, and then you need to convert the x, y into angle, and then you have a much easier way to classify between the r and the theta, using r and theta to have just one single line, and that would tell us where, how to classify the data. Then this is actually one of the most important parts for using neural nets today. A lot of times, the secret sauce is not necessarily the neural net. It's actually how you prepare the data. This is what we call the data scaling, data shifting, and so on, right? So how you massage that data before you feed it into any kind of machine learning pipeline and so on is very, very important, okay? And that's the less glorious part that people tend not to talk about much in their papers. But if you look at practical systems, this data massaging, data preparation part is incredibly important, and they take a lot of time, okay? So when we use different machine learning on different tasks, we have different kinds of features. For image processing, we tend to have these features that are essentially the shapes and so on of these objects. And then for the audio processing, we tend to have features that express in terms of frequency and a spatial frequency kind of shape. And then when we analyze text, we tend to have a kind of a subtree of subject and object and the verb and adjective and so on, so that we will be doing essentially subtree feature matching in the text. So the kind of features that we have in these things tend to be different. And once the question is, which data features are relevant? So, for example, when you detect a car in an image, so in fact, there's currently exactly a competition, a challenge going on right now to detect cars, okay, in all kinds of surveillance and drone videos, okay, just detecting cars. And so cars, have wheels, right? So maybe you should look at the presence of a wheel. But if you look down from above, from a drone, you may not see the wheels, right? So, cars that can we describe pixel values that make up a wheel? Is a wheel, the first thing we think about is wheel is a round thing, right? And then, but think again, what if you look at it from another angle, right? And so on. So you have occlusion, right? Occlusion, you look at from the top, you don't see that wheel. You have perspective, you look at it from an angle, it doesn't look like a real circle. And you have shadows, it may give you the right color, right? And wide wall tires and so on, so you don't have a dark surrounding, who knows, right? So you have all these variations, and so that's why it makes it so hard to comprehensively define what a wheel is like and use the wheel as a feature to find the cars. So that's why we're going to identify these factors of variation so that we can explain the data that we have. So this explainability is actually a very, very important part of all these approaches. So when we have an unobserved object or the forces that affect the observed quantities, then humans use some kind of mental mental process to explain, right? So I look at Carl here, and I don't see a real person. Okay, I only see a head and a little bit of an upper body. So my mental process is, oh yeah, I have a little holding it right here, right? It blocked part of Carl, so that's a real person. Okay, it's not as just a statue, with just the upper shoulder and the head, and also the fact that he's kind of moving a little bit and then he's he's smiling a little bit tells me that he's probably not a fake person or statue, right? So I have this mental process to explain what I'm seeing and so on, and I confirm. But the machine learned things tend not to have that kind of advantage. Okay, they tend not to naturally have that kind of mental, explanation process to convince itself, right? Some kind of iterative approach to convince itself that the observation is correct. So speech, we can have the variations. Every time we hear some words, we need to get used to some cases. Age, sex, accent, words being spoken. And so, there's certain accents that are extremely hard to get used to. But humans actually do it. Okay, so when, I still remember when I was a TA, in the early days, I was, the TA for a professor who has some very interesting accent. And so some of the students will come with some questions. And I was looking at those questions and I said, why are you asking these questions? Also, that's what the professor said. And I go back and ask the professor, why did you say this? It cannot be. And the professor said, no, I didn't say that. And then, so the professor said, oh, this is what I said. I look at that, I look at what the students heard, I said, oh, okay. So there are all these kind of interesting things that, you need to get used to when you adjust. And the cars, position, color, angles of sound. So many of these factors influence what you observe and how you're going to conclude, what that is. So even a very, very simple classification problem can be so complex if you want to get to what they call the tail, okay? The tail of the distribution to be able to get really, really robust, classification. So, so if we don't have, so the grad students in the machine, in the computer vision area used to design all these different perspectives, okay, of these features, so that hopefully they will catch the different angles and so on. There's SIFT algorithms and so on that are designed to facilitate that, right? So, but you know what? The modern approach to that problem is, look, give the grad students a break. Okay, they have suffered enough. They suffered, 3 decades. Okay, so give them a break. Don't ask them to design any more features. Okay, so just use machine learning to automatically identify these features from the data. Okay, from the data. So the data will give you the different angles and so on. So use that, as a feature rather than asking poor grad students to generate all these things by hand. So that's actually the kind of the hallmark of deep learning networks. However, in order to be able to reliably identify these features automatically, you need to really have a huge amount of data. And that's the part that required the computation devices like GPU. So if you go into the public, sort of the popular literature and marketing, the material and so on, you see that GPUs for machine learning, right? And this all roots in that particular kind of foundation. So so machine learning requires the ability to acquire knowledge by extracting these patterns from data, and so this is kind of a little bit of a preview of what you're going to be working on. So we essentially we use a kind of a feed-forward network, and you take a picture, and the picture will go through layers of processing, and the first layer typically will have some basic just the kind of the pixels and colors and so on, and then the second layer will analyze the different parts of the different subsets of the pixels and give you, for example, the edges in your picture. So you would extract the edges from different parts of the picture into the representation, and then the third layer will kind of take the combine the edges from different perspectives and then try to merge them together into corners and then into more. The third one, then the next one will from the corners and edges and then form the objects. So it tries to reconstruct some of the objects and then try to so if you have a training process, the images will go through all these kind of decomposition, and then the final answer says, oh, this is a person. Okay, this is a person. And then you go back and say, okay, so all these objects that I see will lead to a person. So how much weight do I give to these things in order to be able to ensure that when I see something similar to this, it's going to be a person, right, in the future. So that's what the gradient descent process is. You put enough into the weight, into the process to be able to make that decision. So, the next challenge is which data features are relevant. And then we say, okay, we have a hierarchy of these concepts to capture simple and complicated features. If the final set of features is truly the most important one, remember we have these layers, and the layers eventually, the last layer will feed to the output. If the final layer is truly the only relevant part, then you have a very simple, just feed forward, and every layer after one another in the network. But if some of the layers, let's say the edges, are also very important in generating the output, then you have some bypass. You have some things that you need to feed into the from an earlier layer into the final layer. So that's why when you look at some practical models, you see some kind of strange shapes. You have certain layers in the earlier stage that will have to go to a later stage rather than just a simple linear pipeline, right? So you need to learn that hierarchy and learn how important some of these things are. So in summary, the deep learning process will take the input, and input will decompose, will be the training data will be decomposed into the features, and then it will be assembled into layers of abstract features, and then it will be mapped into mapping from features to the output, and then so the training process will learn how important each of these things is in order to be able to make the final decision. And then during the inference, you run the fresh data or the real input through this process, and hopefully all the configurations and weights are learned properly, that it will give you the right answer, right? So that's the summary. So we're going to do a simple thing, okay? So this class is not going to give you every possible deep learning, network and so on. That's not the point. So the point is we're going to be using a relatively simple but incredibly important foundation for all the applications, which is classification. Basically, if you want to do something to an input, you need to make a correct determination of that what input is. And that would be the basis for you to make a lot of transformations and so on. So this is kind of the required first step for almost all the applications. So formally, classification is a function that maps the input of k categories into a input into k categories. So we have a number of potential outcome. Okay. So the person, scissor, and bicycle, whatsoever, right? Nails on the road, and debris and so on, right? And the potholes, right? So those are the things that you probably want to classify in a self-driving car situation, right? And then you have Rn, which is input, which is essentially depending on your modality. You have a camera, then it's pixels, but then you may have an infrared detector, so that will be some kind of pixel map, but that's not exactly the same pixel as your images. And then you could have some kind of a radar, right? So these are the they all give you some sort of pixel map, and then you need to map from the pixel map into into one of those categories. So basically, in a kind of a deep learning kind of network, the definition is you take the input, okay? You take the input, which is x, and that could be the pixels, right? And then you take everything that you learn in a network in terms of those weights, okay? So that's the data that we're seeing here. So the combination of what you prepare in the network and the input pixels should give you an outcome, okay, a conclusion. So theta should encapsulate the structure as well as the weights that you put into these things, such as the lines that you learned and so on, right? So let's start with the simple thing, okay? The most simple classifier is drawing a line, and then, you know, this is classic, you know, this is just statistics, okay? People in statistics do this forever. So, you know, you have essentially y is equal to the sine of w, you know, dot x plus b. What does that mean? Essentially, when you have a coefficient times x plus a constant equal to y, it defines a line, right? So, you know what? So if you learn all the you know, w values for the vector, and then you know, and you have the bias, then you can just draw that line, and that line will separate, you know, one category from another category. So this gives you a binary decision, right? A binary. So you classify things into two categories, right? So here, you know what? Essentially, the line is defined with a slope, right? And then you know, these points. And remember, this is a very simplified view. X in this case is a scalar, right? You have a scalar value, right? X, and then W is going to be a single coefficient, right? B is going to be a scalar coefficient, right? So then you know, you can get a Y value, and the Y value, you know, whether it's greater than 0 or less than 0, you can normalize it so that the greater than 0 or less than 0 gives you the classification, right? So that's a very simple thing. But the X in general is a vector, right? So the vector gives you a high dimensional space. So this line that we're seeing here is really just, you know, is actually a hyper surface, right? That cuts into the a high dimensional space that classifies all the data points in the high dimensional space. That's really what it is. So how do we do this? Well, this is actually quite easy. So X is a vector, so we have all the X values, you know, elements of X feeding into the network, and W is the coefficient for the vector space. So, you know, every you know, element in the vector will have a different W, and then you do the addition, right, with the bias B here, okay, the bias B. So this is a scalar here, and then you determine whether it's, you know, it's yes or no, right? And this goes back. Remember the age, right? The age and you know, the net worth, and then so if you do the angular radius, you know, the coordinate, the B shifts you to the middle of that little, you know, the little sphere thing, and then the R gives you, you know, the W gives you that R, and then you can determine whether it's, you know, in there or not. So this calculation is a linear classifier, is a dot product, right? Because it's every X value is multiplied by a W value, and they get added together. Does that sound familiar? We have seen this dot product many times. Matrix multiplication, convolution, right? So this is the fundamental reason why, you know, dot product is so important, because, you know, in virtually everything that we consume, somehow we do any kind of linear prediction, anything, we end up doing a dot product, okay? So you know, so you're going to see that again and again. So the dot product and then a scalar addition, that's why, you know what, you know, there's a name to this, you know, it's actually, you know, inner product, and you know, there's a you know, standard library function that does this in you know, practical systems. So we are right at, you know, the 10:50. So what we're going to do is we're going to the next time is we're going to start with the multi-layer perception, and then we're going to derive ourselves into the neural net, okay, formulation. And then we're going to go into the actual computation that we're going to implement for the neural net. Okay? So see you next time on Tuesday.